ExaNeSt invests in innovations to ease the journey to exascale supercomputing. The project's founders identified that in high-performance computing systems, more energy was being consumed in the movement of data than the processing of that data. Energy efficiency is the main barrier to producing an exascale supercomputer. An exascale supercomputer is 30 times as powerful as the most powerful system today. But is expected to use less than 2 times as much energy, requiring developments to improve energy efficiency 15 times. The project vision has been to reduce the distance traveled by data within a supercomputer. This is done by distributing the data across the system, making communications more efficient and condensing the electronics into a smaller space. Key project areas are interconnect, storage, packaging, and applications.
So Nicholas, can you tell me about the interconnect for ExaNeSt?
Okay, for interconnect, we're building a unified low-latency interconnect with an efficient hardware transport.
So why low latency?
So low latency is so important in HPC because applications with a low latency interconnect, they can run smoothly and more efficiently so that they can run with less energy consumption.
And then why unified?
Okay, for unified, we merge the storage and the computation traffic onto the same infrastructure, the network infrastructure, so as to reduce the acquisition cost and also the energy bill that you pay every month.
So can you tell me about the storage part of this project?
In ExaNeSt, we use BGFS, an European parallel file system that has a unique feature that you can bring up a partition on the fly. We use this particular feature with a new developed one about resilience in order to speed up the application by localizing the storage and to consume less energy.
Did you use real applications to test the ExaNeSt prototype?
Yes, in ExaNeSt we used a real application, going through brain simulation, cosmological simulation, computed fluid dynamics, and data analytics. We had the opportunity to test this new designed platform and see that we can gain up to 6 times energy to solution.
So what was the result of your re-engineering the applications?
Re-engineering the application specifically for example, for the FPGA gave us the results that we can run at the same speed as a modern GPU with less energy.
So why is density so important?
Density is important because you want electronics, your computations to be at a short distance so that communication is faster and consumes less energy when those processors collaborate with each other. Plus, you reduce the size of the supercomputer so that the housing room facilities cost less.
So how does storage work with this density in the ExaNeSt?
Storage traditionally was further away from the processor and memory, not in our system, because nowadays storage is quite faster. You want it to be right next to the main memory and to the processors so as to reduce communication distance, time, energy again.
So this project really centered around energy. What were the accomplishments?
We have demonstrated that we can solve important HPC problems consuming up to 6 times less energy if you solve them in this new environment. Plus, we have made many of the steps that are necessary to port HPC to this new environment by implementing a real working HPC testbed.
Now to show you about the project prototypes. This is the project's compute board. It's not much larger than a drinks coaster, but it has 4 processors and 4 fully reprogrammable accelerators. The underside of the compute board includes a loadout of 4 SO-DIMMs of RAM, which can be error correcting, and an M.2 SSD. This is the air-cooled prototype. It includes compute nodes connected by a completely custom interconnect. The compute nodes were then migrated to this liquid-cooled prototype. Each blade contains 4 compute nodes. The heat produced by the compute nodes encourages natural convection currents that take the heat away. Each blade can quick disconnect in and out of the prototype to enable service and maintenance. The output from the system is water up to 50 degrees centigrade, enabling it to run without active refrigeration. At 50 degrees centigrade, the heat can be effectively reused in heating systems. The ExaNeSt project is funded by the European Union under the FET-HPC Horizon 2020 programme. The project consists of 12 partners from 7 EU countries, contributing over 1,000 person-months of effort over a 3.5-year period. To find out more about the results of the project, visit the ExaNeSt website. To find out more about how the results are being used in the future, visit the EuroExa website.